thanks for coming out yet again. As you know, this is our last lecture today, so I'm hoping you guys enjoyed the series, and it's been a lot of fun for me and a learning experience. So we'll just go on for today then. So today's topic is future accelerators and detectors. Of course, the whole series has been about what other uses we've come up with for particle accelerators and particle detectors. Talked about how they show up in cancer diagnosis or national security. And so for the last lecture today, I want to talk about what's the future for accelerators and detectors. I'm not talking about future applications, I'm just talking about where is the technology going. Now, you can imagine this is a huge field. There's a lot of people working on all sorts of different accelerators and detectors that might be used in the future. So for today, I'm going to focus on one particular aspect of those technologies, and to unify the talk and to talk about both an accelerator and a detector that uses this topic. I've chosen plasma, plasma-based accelerators, plasma-based detectors. What plasma is, I'll get into this in a few more minutes, but it's basically a fourth state of matter. And it's got a lot of applications. Today what we're going to talk about is a detector, a particle detector that uses the same technology as plasma televisions. And we'll also talk about a particle accelerator that uses plasmas in a completely new way to really get huge amounts of acceleration for electrons and maybe in the future protons as well. So to get this thing started, we need to talk about plasmas and what they are. And as I said, plasmas are a fourth state of matter. So I kind of had a little nerd happy moment when I saw this picture, because this is a picture of all three of the common states of matter at the same time. So what you're actually looking at is the chemical argon. This is extremely cold. I think they cooled it down using liquid nitrogen and something else, but I forget the temperatures involved. But the neat thing is you can see, the thing they're holding that looks like ice, that's of course the solid form of argon in this case, and you can see it dripping out in liquid form, and then you've got some sublimation going on, giving you argon gas. So these are the three states of matter that we're all generally familiar with. And just to make sure we're all on the same page, let's talk about how you transition from one state to the other. So if we start with a solid, this for example is a crystal structure. You have, it's very rigid, it's got a regular pattern. Not all solids have a regular pattern, but they're rigid. The atoms and the molecules are not moving around very much. They're not moving past each other. So what's happening here is, besides being locked into this rigid structure, each of these atoms is vibrating a little bit, just due to the ambient temperature. And as you dump more temperature into it, these things are vibrating more and more frequently, more and more energetically, until they actually can overcome the interconnected bonds between them, the interatomic bonds. And so once they do that to a certain extent, then of course they turn to a liquid where they're still somewhat bound. They're not flying off in all directions, but they're certainly not as rigid as they were. You've got atoms and molecules that are sliding past each other. They have some more freedom of movement. I'm going to hurt myself if I don't watch out here. All right. Okay, so we've got a liquid. You keep dumping more heat into it, and eventually these vibrations of the individual atoms involved become so strong that they can become unbound and fly off in all directions. And this is what we know as a gas. There's very little interactions between the different atoms or the different molecules of a gas. They're just kind of bouncing off of each other and going off in some other direction. So I think we're all pretty much familiar with these phases of matter. We talk about this in probably elementary school at this point. So then the next question is, well, what happens if you keep heating this up? You can still dump more heat into a gas. What happens? Eventually, the vibrations, what I was just talking about was vibrations of an atom as a whole. But of course, an atom has pieces to it, and it's got electrons and it's got a nucleus sitting in the middle. And so these things are also vibrating due to the temperature. And if you keep increasing that temperature, eventually some of these electrons are going to pick up enough energy to just exit the atom. And then you get what's called an ion. What's left over has a positive charge because the negatively charged electron has gone off in some direction. And so, if you heat this up to the point where electrons and ions are no longer bound together so tightly, you end up with something that's still technically a gas, but it's, for example, a neon sign. So it's technically a gas, but it has free unbound electrically charged particles. It's got the electrons and it's got the ions. And when you have freely moving charged particles, you can conduct an electric current. And so that's, for example, what's going on inside the neon sign. So you have this fourth phase of matter, this gas of electrons and ions that can conduct electricity, and you can use that to, say, light up a neon sign or a fluorescent light or a plasma TV. So what kinds of temperatures are we talking about here? When temperatures, or when you start talking about atoms and electrons and ejecting electrons, typically we don't, the vocabulary isn't so much in terms of temperature, it's in terms of energy. How much energy does it take to do this? But the energy does, in some sense, correspond to a temperature. So when you're ionizing neon, when you're ejecting out the outermost electron, one of the outermost electrons, that corresponds to a temperature of about 450,000 degrees Fahrenheit. Now, of course, your neon sign is not operating at 450,000 degrees. It would be fatal. So what's actually happening here? Most of the gas in this sign here is not a plasma. Most of it is just regular old gas. There's just a thin kind of channel where the voltage is high enough to strip off electrons from some of the atoms. And as long as you get kind of like a chain of plasma, a very thin channel of plasma going through, that's enough to light up your sign. So these things only heat up to maybe a few hundred degrees, not hundreds of thousands of degrees. And that's because most of the atoms in here are not in plasma form. But the part that's making the light, that is plasma. So to actually do this, what you end up doing is you need a little bit more. You can't just use plain old neon and hope for some light. You need a little bit of an impurity in there that's going to emit visible photons. So, for example, the other technology where this is used is in fluorescent lighting. What you're looking at here is basically a fluorescent bulb without the inner coating on the inside. And what's going on here is you've got a very small amount of plasma being created. It's sending electrons through a current, and in a fluorescent bulb, what they do is they put in a little bit of an impurity. They put in some mercury vapor, and what happens as those electrons flowing through the plasma collide with the mercury atoms, they excite them a little bit, and then when those mercury atoms go back to their ground state, when they lose the energy that was added to them, they're emitting ultraviolet photons. So actually, this lamp is from like an antibacterial, or it's supposed to kill bacteria with ultraviolet light. If you want to make a safe fluorescent lamp out of it, you just coat the internal wall of this with just some fluorescent material which absorbs ultraviolet photons and emits visible light. And so that's how we use plasmas for lighting. Is there anything else special about plasmas? So unlike regular gases are neutral. They don't conduct electricity. You can't do much to them with magnetic fields. But plasmas are different because you guys all seen stuff like this, these little novelty plasma lightning balls. But you can see some of the complex phenomena that you get with plasmas that you don't get in regular forms of matter. So what's happening here is this is a gas that can be affected by electric fields, and it can be affected by magnetic fields. But not only that, because the things inside the gas are electrically charged, they also can change electric fields and change magnetic fields. So you can get these complicated feedback loops going back and forth. You get complicated behavior, and you can see some of that here, like filamentation. You can get like sheets. So there's all sorts of neat stuff that you can do with plasma. It's a much more complicated form of matter than say just a regular gas. So this is the fourth state of matter. This is plasma. What do we do with it? The first thing we're going to talk about today is making what have been called plasma panel sensors, and these use basically the same technology as plasma televisions. So the first thing we're going to talk about here is how does a plasma TV work? Because once you understand that, it's only a short jump to understanding how a plasma-based particle detector could work. So plasmas have actually been around since the mid-1960s or so. This is a plasma display from, I think, the 1970s, just to show you that these things have actually been around for several decades, even if they haven't been widely used. So how does a plasma display, a plasma panel, actually work? This is a close-up and a kind of a cross-section of all the pieces that go into it. Of course, the main part here are these cells just these little tiny cells. You get millions of them in a single display. They can be down to about the size can be down to about the width of a human hair. I don't think those are in consumer TVs, but I heard something like the military has made finer plasma displays. I don't know what they use them for, anyway. So what are these little cells? They're little hermetically sealed, self-contained, basically gas chambers, and they're filled with some inert gas, either neon or xenon or argon or something. And they have just a little bit of mercury in them also to emit ultraviolet light and have that ultraviolet light hit phosphors, different colored phosphors here, and emit visible light of different colors. So one pixel would be this unit that's kind of outlined in black, and of course it's got the familiar red, green, and blue components that have been in standard TVs since. For decades now. All right, so that's what a plasma TV is made out of. So how do you actually light up one of these cells? Well, you see these yellow strips running horizontally here, vertically here. These are just metal electrodes. And what you do if you want to activate one of these plasma pixels is you charge up a pair of these. You put a voltage on them. So let's say we want to light up this blue one here. We're going to charge up this strip, and then we're going to charge up this strip here. And where they overlap, there's going to be enough of a voltage across that cell to start pulling electrons out of the neon that's inside these cells. And you charge that up enough to basically initiate a plasma discharge. Once you separate enough of those electrons from the ions, you have enough free charges to conduct a small current. So in a sense, there's like a little lightning bolt or something inside the cell. You get, again, electrons hitting mercury. Mercury emits ultraviolet light, and then that ultraviolet light hits the phosphorescent coating of that cell and emits visible light. That's basically all there is to plasma TVs. Now it's a lot, you've got a lot of electronics that have to go into getting all of these, addressing all of these cells quickly and correctly, and you don't want something happening in one cell to affect what's happening in another cell. Your colors are going to get messed up. So there's a lot of engineering here that I'm glossing over, but that's the basic the basic way of making a plasma panel and making a picture on something like a plasma TV.
What's the dielectric?
Sorry?
What is the dielectric?
Oh, what's the dielectric? It's, I want to say magnesium oxide. I'm not 100% sure. I think that's right. Yeah, Howard?
Is there a impurity that'll work besides mercury?
Probably, yeah. The mercury is the one that I heard of in terms of being used most often. There may be something safer. I'm not sure. I'm not sure. There's probably something else you could use. All right, so this is how we get a plasma TV image. Now, how do you take this and turn it around and make a particle detector out of this? I had a paper. I get a daily email of new papers about particle physics that comes through, and I can check what's happened in the last 24 hours. And back in April, I think it was, I saw one that said something about plasma panel particle detector, and I was like, what the heck is that? So it was actually this technology where they were able to turn a plasma TV into a particle detector. So why would you want to do this? Well, first of all, why would you even be interested in making a particle detector out of a plasma display? It's a tested technology that's really mature, and just to give you an idea of how far it's come, this was one of the original prototypes for a plasma display back in 1966. Professors Bitzer and Slotto at the University of Illinois actually came up with the first plasma display, and the plasma part of it, you see this little bright N-shaped thing here. This was the first one. So it's come a long way since then. Just for comparison, this was 20 years later here in 1987. You can see how far the technology had improved at that point. And then, of course, now all you have to do is walk into Best Buy or Costco or something. You see walls and walls of plasma TVs. So this is something that makes it attractive for many uses, but of course, from my perspective, for particle detectors, you want something that's, if you have a tested technology that's available, you don't have to do a lot of engineering on it. That's obviously attractive. That makes it cheap also. You can produce these things for about 30 cents per square inch. And that number might be outdated. It might even be cheaper now. They're durable. They're long-lasting. The components don't really age. There's not really any moving parts. I suppose the electronics could wear out, but if you construct it well, you can hedge against that. I mean, they've got plasma displays that were created in the 1970s that are still operating today. Another nice thing is, it's got a gas. The gas is really going to be the core of how this detector works. And in a lot of gas-based detectors that we use in particle physics experiments, you need a big gas circulation system to keep things moving, flush out impurities. But with this technology, each of those little cells is hermetically sealed. The gas doesn't have to go anywhere. And since you're picking an inert gas like neon, one of the noble gases that's very non-reactive, it's not really going to change much over the course of 5, 10, 15 years. The other nice thing is that this is getting more onto the detection side. What makes it good for detectors is that you can get very good spatial resolution. If these cells are the width of a human hair, that tells you something about the accuracy with which you can see a particle going through it. They also have very fast timing. You can get a signal in about 10 trillionths of a second. So these can be extremely fast. So we're going to go back to the picture here, and instead of talking about how this is going to be used for a TV, what changes do we have to make for this to become a detector? All right, easy one. First of all, we don't need the phosphorescent coating. We can get rid of that. We don't care about making images. What we are going to do, though, is we're going to charge this thing up now. Instead of trying to initiate a plasma discharge in a cell that we pick, what we're going to do is we're going to charge the whole thing up, but just to under the voltage where you'd get a plasma spark. You want to get it just about there, but not quite. And the reason for that is, as soon as an electrically charged particle passes through this and knocks off an electron ionizes just a little bit of that gas, it's going to set off a chain reaction. You've got the voltage cranked up just enough so where you add just a little bit more energy and you can get your plasma discharge. And then instead of using these electrodes to activate a cell, these electrodes are going to read out the signal. They're going to see the current from that spark. And then based on which pair of electrodes show a signal, you can tell which cell fired. And so that tells you where your particle went through. So the neat thing about this is it can sustain rates of particles going through it. You can get up to a billion hits per square centimeter per second. I mean, these are fast. So there's another change that needs to be made though. I said these things are extremely tiny. You can actually have they have really advanced plasma displays now that are about a millimeter thick. They're really, really thin. And it turns out having super thin plasma displays is not quite as useful for particle physics. The reason is we need to give particles passing through enough room to actually ionize some of the gas molecules here. If this space here is too thin, if it's 1 millimeter or less, there may not be enough gas that the particle passes through to actually ionize something and create your signal. So what you actually need to do is raise the thickness here. You have to raise the height of the cells basically to about 3 millimeters. 3 millimeters will ensure that some particle going through has a 99% chance of ionizing at least one atom along its path. So we actually have to back off the miniaturization a little bit if we want to make a particle detector. The last thing we want to do is make sure you don't get too much electric charge building up on these outer planes, these so-called dielectric planes, which are insulators basically. They're electrical insulators. And they can actually get charged up with all of these electrons floating around in here. In a plasma TV, you actually want to maximize with this so-called wall charge. The reason is you want to make electrons freely available so that when you address that cell, it lights up quick and you get a fast response to your TV. But for a particle detector, we want to make sure that it only gets activated when a particle actually passes through it, not when some electron sitting on the wall happens to fly in and maybe kickstart your discharge without you actually, without a real high energy particle going through. So what you need to do is actually minimize that wall charge. That's not actually that hard because plasma TVs have an option to erase a cell or turn it off basically, and you want to just remove the charge from it, remove the voltage, and calm everything down. So that's something similar you can do here, where either periodically you could just erase all of that charge, or periodically, when a cell fires, you can send an erase signal to it. So that's basically how you take a plasma TV and turn it into a particle detector. So what could this be useful for? In my experiment, Atlas, one of the obvious uses for this is putting it in our muon detection system. This is, if you remember, actually now it's 3 weeks ago with our last lecture, so I'll remind you a little bit. The outermost layer of our detector was the one that detects muons. These are the heavier cousins to the electrons. You get a lot of them in particle physics experiments. And the reason it's the outermost layer is because those are the only particles that are long-lived enough to pass all the way through the detector, and they also don't interact enough to get absorbed along the way. So that's your outermost detector. And since this signal that I'm talking about is just on or off, it's digital, you only know whether something passed through it. That actually makes it ideal for detecting muons, because those are the only things that are going to make it through to the outer part of your detector. So if you see something, you say, okay, that was a muon. And because the timing signal is so fast, you can actually use this as part of your what's called your trigger system. And what I mean by triggers here is to trigger whether you want to write your data to tape. You might remember if we're getting 40 million collisions a second, and we can only write 200 per second onto disk, we need a very fast trigger system that can analyze data in real time and make decisions. So, so it's conceivable that this kind of technology could be used for that purpose. Maybe not in my detector, maybe in some other particle physics detector that's to be built yet. All right, so where is this currently in real life? There are the University of Michigan, for example, is working on this with some private company. This thing is patented, so that's in the works. They have prototypes. Right now, the last I heard, they're testing out gas mixtures, different types of gases inside the cells, and also different pixel sizes to see what you actually need for a real particle physics experiment. So this is actually becoming a fairly mature technology for particle detection. I wouldn't be surprised if I started seeing something like this even within the next 5 or 10 years. Maybe early, well, maybe not earlier than 5 years, but 5 to 10 isn't great. So, so this is something that's kind of short term in terms of how far it's advanced. So, so that's it for the detection side. That's how we can use plasma displays and turn them around and make them into plasma-based particle detectors. The next thing we're going to talk about here, and this thing's really kind of sci-fi, or well, it's not the fi part anymore, it's not fiction, but it seems really futuristic to me, and you can get really cool pictures like this. This is actually from a simulation. So there's this technique called plasma Wakefield acceleration, and it's a completely new way of accelerating subatomic particles. And so before we get into this, the first thing we're going to do is review standard acceleration techniques. How do we accelerate electrons and protons currently? The basic technology is shown in these two pictures. This thing here is called a Klystron. I think I showed this in one of the first lectures. It's basically a generator of microwaves or radio waves. And what this does is it provides the energy to accelerate charged particles. And what does it do with this radio wave energy that it's generating? It sends it underground to where the particle accelerator actually sits, into one of these so-called RF cavities. That stands for radio frequency cavities. These are things that are that resonate with radio waves. So you can actually pump a good bit of energy into it and use that energy to accelerate, say, a bunch of electrons or a bunch of protons as they go through. In this case, this thing's for accelerating protons. This is what they use at the Large Hadron Collider. So how do you, what do you do with these? You take basically a bunch of Klystrons and a bunch of RF cavities and chain them together. Because what's happening is, at each time, actually before I get to this, whoops. Each time you pass through one of these cavities, say if you're accelerating protons, those protons are going to see a wave in that cavity. And if you get your timing right, they're only going to see the part of the wave that accelerates them. They're going to see the part that gives them a push. It's in a way, it's like surfing. They're keeping right at the wavefront as they go around and around the LHC ring. And each time they pass through one of these, they get a little bit of an energy boost. So you can see the two types of accelerators here. For example, this is the linear accelerator. It's slack. It's a 2-mile-long straight line. And then you've seen this picture before. This is the Large Hadron Collider near Geneva, Switzerland. I was actually kind of surprised when I started looking up some of the details of how these different experiments, or these different accelerators use Klystrons. At SLAC, at this linear accelerator, they have 250 Klystrons spread out along this 2-mile-long linear accelerator. And each of those Klystrons, high-powered radio wave or microwave generator, I keep saying radio and microwave because it's kind of on the border of those two ranges. But each of those Klystrons can output a pulse. It's a very short pulse, but it's 65 megawatts of power going through. They've got 250 of those. I was really surprised when I looked up what it is for the Large Hadron Collider. Each beam of protons here, so there's 2 beams, each one has only 8 Klystrons, and they're only about 300 kilowatts. And when I first saw this, I was like, what's going on there? This is the most powerful accelerator on the planet. And of course, the difference is you've got a ring here. You can go around as many times as you want. So you don't need necessarily a lot of Klystrons, and each Klystron doesn't necessarily need a whole lot of energy, because you can just go for another pass and just keep adding more energy to your protons. Here at SLAC, where they just have a straight line, you only get one shot. You have a few microseconds to pump in as much energy as you can. So they need a lot of Klystrons, and they need to be high-powered Klystrons to get all of that energy in just a few microseconds. At the Large Hadron Collider, we can take things a little more leisurely. When they're ramping up the proton beams to full power, that process can take 45 minutes. And the protons are going around here 11,000 times a second. So you have a lot of chances to pump in that power. All right, so these are some current accelerators. And what about future accelerators? You can see a size comparison here of Fermilab. This is actually a picture of the area around Fermilab. This little blue circle here is the main ring. It's what is it, about a mile across, I think. You, of course, compare that to the Large Hadron Collider, much bigger. And then there's this proposed International Linear Collider, which right now they're thinking it's going to be something around 20 miles long. Why does it have to be so long? Well, okay, the reason it's linear, first of all, is because they want to accelerate electrons. We talked about this a long time ago, but the basic punchline is for electrons, you want a straight line accelerator. For protons, you want a circular one, and it has to do with how much energy particles lose when they go around in a circle. Protons don't lose that much, but electrons lose a lot when they're accelerated at high rates in a circular track. So if you want to accelerate electrons, you need a long, straight accelerator here. And the reason this thing has to be so long is because, remember, if it's linear, they only get one shot to accelerate these things, and there's only so much power you can pump into Klystrons and RF cavities. At some point, an RF cavity can only handle so much energy pumped into it, and at some point there's going to be what's called a breakdown. The thing can actually, it can literally break, or it can just stop working. It can stop resonating with radio frequency waves. So there's an inherent limit to that technology. And right now it gets you, you can pump in about, or you can get to electric fields of about 10 million volts per meter. That's about the limit of that technology. And so if you want to make a really high energy electron collider, it's just got to be long. Unless you have some completely new way to do your acceleration. Because what we have now is just about maxed out.
Tennis player on each end.
Sorry?
A tennis player on each end.
Tennis player on each end. You have to have a lot of steroids. But fortunately, we've got another way. It's not as cheap as hiring tennis players, but you can use, of course, the topic of this lecture, plasmas. All right, how is this going to work? You take just a tube, can be maybe on the order of meters long for what I'm going to talk about in the next few minutes. Fill it with a gas. The type of gas isn't so important, but we'll talk a little bit more about it later. And what you do is you take a high energy bunch of electrons and shoot them through that gas. And so before the electron bunch sits in, you've got your atoms here. I grabbed this picture from Symphony magazine. So at this point, pretend these things are bound together. These are not. This is not a plasma here. This is just a regular gas when this thing goes on. What happens when this bunch of electrons goes in at a really high energy? The front of this bunch is going to push all of those electrons in the gas out of the way. They're just going to come barreling through and push these electrons out to the side. And of course, the reason the electrons move and not the heavier ions is because the ions are so much heavier. The atomic nucleus is many times heavier than the electron. So the lightest things, the electrons, get pushed out to the sides, and you're left with this kind of column of positive charge in the center. Now, for this split second, this moment here, you do have a plasma. You've freed the electrons from their atoms, and they can push off to the side, so you have a plasma, but it's kind of a very unbalanced plasma. You've got the core of it has positive charge, and right on the periphery you have your negative charge. So what's going to happen, of course, these electrons are attracted to the positive charge. They're going to want to crash back in. And they do that in kind of a wave pattern. Because as this thing goes by, it's knocking them out, point by point, and so they're going to come back in kind of an organized, semi-organized fashion. And this is really the same thing that goes on when you see a boat go by and it pushes the water out of the way, and then behind it, the water crashes back and leaves a wake. So that's why this technique is called plasma Wakefield acceleration, because you're using this wake now of electrons crashing back. And right when they come together here, in the back of the electron bunch, you can get actually extremely high electric fields, much stronger than anything we could generate using the Klystron RF cavity combination. So, I forgot I had another picture of it. This is from a paper that was written by a group at SLAC, and so you can see in a little more detail what's going on here. You've got your pulse of electrons here. This color coding is giving you these positively charged ions out here. So this is the front of it, this is the back of it. And these plasma electrons now, as they come crashing in the back, that's where you get your what they call your peak accelerating field, your maximum electric field for acceleration. So, so I'm going to talk about actually what this group at SLAC did. They did a demonstration of this in 2006. And what they did was they filled a tube with lithium gas, let's see, it was about a 1,000th density of air, so it was mostly vacuum, but there was just a little bit of lithium gas in there. And this tube was only 85 centimeters long, so keep that in mind. This is going to be a benchmark that we're going to want to remember later. And what they did was they injected an electron pulse that had been accelerated to the full potential of what the SLAC linear accelerator can do. And that's 42 billion electron volts, 42 GeV. It's several hundred times smaller than what the Large Hadron Collider can do. But anyway, that's the most that they can do at SLAC. So they cranked that electron pulse up to its full energy and just crashed it through this lithium here and created this plasma wake pattern that we just talked about. And what they found was, as the wake closed and came back on the electron bunch, the electrons at the tail of the bunch, the ones closest to that peak accelerating field, really got a boost. And what you're seeing here is the final energy they got out of this pulse as it came out of this 85 centimeter tube here. Now most of the electrons were still down here at 40 billion electron volts, 40 GeV, 42. You can see some of them lost energy. That's from collisions inside the plasmas, and also they might have lost a little energy afterwards, but most of it was probably in here. But you can see here, some of them got accelerated to 50, 60, 70 GeV. The most they measured was about 85 GeV. So what does that mean here? That means it takes 2 miles with conventional accelerator technology to accelerate electrons to 42 GeV. And then you add an additional about 42 GeV in 33 inches. I mean, this tube was only 85 centimeters long. So 2 miles, 33 inches. That's a pretty neat technology. I mean, this is something that I've heard it compared to the difference between computers based on vacuum tubes and computers based on transistors and modern computers. So I mean, it's really a huge compression, and it could allow you to build much smaller accelerators. So I'm trying to remember. I think there. Oh, the one other thing though to keep in mind is that the intensity that you see in this picture here, the brightness is proportional to how many electrons got that boost. So you see up here around 85 GeV, it's a very small number that actually got that boost. Most of them are sitting down here at 40 and below. So it's not the most efficient way of doing it, but it was kind of a proof of principle. This is a demonstration that you could, for some of the electrons in that bunch, you could double the energy in, something in 33 inches. It took you 2 miles to get there initially, and then 33 inches to double it. So so I mean, even that gives you some hope that once this technology matures a bit, you can really instead of building a 20-mile-long linear collider, you have the hope of being able to build it much smaller. Of course, that's got all sorts of practical benefits in that you don't have to dig a 20-mile-long tunnel. You don't have to deal with multiple municipalities, trying to get politics involved in all of this. It could be a real big help here. So, all right. So, bottom line, in 33 inches, they doubled what you can do in about 2 miles with conventional technology. So, where else could this technology go? There's a couple other ways of doing this. This is a computer simulation of instead of using just a single bunch of electrons passing through your plasma, you might send what they call a pilot bunch, an initial bunch of electrons to create the plasma, followed by a separate bunch of electrons to be accelerated. This might make things a little bit cleaner so you don't have this long range of energies being produced. You have at least 2 pulses that might be more cleanly isolated. Your pilot bunch and your accelerated bunch. The other way you can do it is without using electrons at all to start the plasma. You could just create a plasma and then use, this is what a team at Berkeley is working on. They start with a pre-existing plasma, which they've created through some conventional method, and then they use lasers to set up electromagnetic fields in that plasma. And this is one of the things that makes plasma special, remember, is that you can manipulate it using electromagnetic fields. So what they do is they use a laser to set up this plasma wake, and if they can time it correctly, again, all you need to do is make that plasma wake somehow, and then you can send in a bunch of electrons and accelerate it. So these are ongoing developments with this sort of accelerator technology. It's not as advanced as, say, the plasma TV detector technology. This is something that might get bigger, maybe in 10 years or so. I'm not sure about that. Certainly, I'd be really surprised if this was getting more ready for prime time within 5 years. I think that's maybe a little bit short. But this does offer hope in the future for building much smaller accelerators, and that's going to bring down the cost and just make it so that really we don't want to build a 20-mile-long accelerator. So, all right, so that's what plasma Wakefield acceleration is. So, so to summarize, today we talked about how plasmas, as you see like a lightning bolt here, this is a Tesla coil over here. We've seen how plasma can offer a way to build better accelerators, to build new detectors. And of course, remember, this is by no means the only future technology out there for accelerators and detectors. We talked about this because it allowed me to talk about 2 separate things using only having to explain plasmas. And I think from this, it's kind of clear that it's becoming clear that crosstalk between different fields is what's really driving these innovations. I mean, the engineering of plasma-based TVs, the engineering expertise of plasma TV makers can be translated over to the realm of particle detection. So that kind of merging of the fields leads to maybe a new way of detecting particles. And of course, the fields of plasma physics and traditional accelerator physics are normally pretty separate, but if you put them together, you can get this huge amount of acceleration using a fairly small setup.
Can you explain this?
Can I explain what's going on in this picture? This is I believe this is, I'm not sure if this is a laser pulse. This was from the laser acceleration thing. So I think this is a laser pulse setting up the plasma wake, and the actual place where the plasma is crashing back together is down here. Yeah, this is where you get your accelerating field. Yeah, this is from a computer simulation, but it makes nice pictures. So, all right. So to summarize, new detectors from plasma, new accelerators that can give you factors of thousands more than what we can do with traditional particle accelerators. So that's it for today's talk. Before I take questions, I just want to say that I opened this series by saying that I and many of my colleagues, I think, are in this game, particle physics, because we want to understand how the universe works. We're we're just curious about it. This is why I'm doing this kind of work, is because I just want to find out what's going on. How does the universe operate on the smallest scales? I think a lot of us feel that this type of knowledge that we're working on, this is going to be our greatest service to humanity. But that's not the whole story. To do our investigations, we have to build technologies to extract information from the smallest scales in the shortest times. And while we're doing this, I think most of the time we're not thinking about how these devices might be used to diagnose cancer, or clean up the environment, or be used for national security, or advance worldwide communication like the World Wide Web. We're not thinking about that most of the time. But those have been the offshoots of doing this kind of research, of the tools that we use for doing particle physics. So I hope that over the last couple of months I've convinced you that the study of particle physics is useful, not just in its own right, but even if there are no direct applications of these research goals for decades. And one point I haven't really mentioned so far, I've talked with you a couple of times about this, is funding. A lot of other fields of science have a combination of public and private funding. And in particle physics, we don't have that. Essentially, all of our funding comes from public sources. So, my salary is more or less paid by your tax dollars. And all of particle physics really is only funded by the public, because private industry is just not interested in stuff that may have applications 20, 30, 50 years down the line. So since that's the case, from my perspective, I consider it basically a responsibility for us to report back to the public on what it is we're doing. Now, I happen to enjoy this kind of stuff also. I enjoy talking to you. When they told me, we're going to fill a room with 100 people or so and you can talk to them about physics, I was like, okay. But I do, since you are funding our research, you should have some stake in it. You should understand what we're doing with it, both on the fundamental research side and on the application side. And we really need to do a good job of keeping the application side in the forefront. So for me, it's been an honor to have given this series, and I'm pleased that you all turned out week after week to hear me talk about particle physics technology. And I appreciate being around so many people who love science as much as I do. So thanks for your enthusiasm and your curiosity. We do have a luncheon in about 10 minutes, so I have some time for a few questions about this topic, or we can open it up a little bit more. And keep in mind, please, if you're leaving the room, please just try to do it quietly so I can hear everyone. So you had your hand up real quick. Yeah.
Pushing up the electron.
Yeah.
That is remind you of anything. Is the theory of Aristotle of movement.
I'm not familiar with this particular theory.
Aristotle thought that movement in the vacuum was impossible because the air moved by the project side in the way keeps pushing it.
Huh.
And now
this is similar, yeah. It's in a way, all right. It's a nice parallel, yes.
Can you repeat the question?
Sorry. The question. Sorry, that might have been quiet. The point was that this plasma Wakefield acceleration looks apparently something like what Aristotle has said about how movement works. And I guess the claim was, he was wrong about saying that movement couldn't occur in a vacuum. It certainly can. But the method of movement, say through air, I guess, was the idea that it was coming back around the object and giving it a boost from the back. That theory is not technically correct, but it's similar to how this plasma Wakefield works. So that's kind of neat.
But it's very, very, very identical to this.
The concept is, sorry?
The gun that the projectile goes through the barrel of the gun and ignites the fuel behind it, which is the propellant.
Sure. Yeah. Think about that one. That might be right. All right. So Howard. Yeah.
Any hope for Fermilab and these plasma-based devices?
I have not heard any talk of these being used at Fermilab. Now, I'm not going to go say it won't be used there, but it really depends on what happens with Fermilab in the next few years. At the moment, they're moving away from what's called the energy frontier of really high energy physics, and they're looking more towards neutrino physics, which is interesting, but you can do it at lower energies. That being said, I think if you can build accelerators, really, full-scale accelerators using the plasma technology, I think in the end it's probably going to be cheaper and easier. Probably easier to build. I don't know about easier to run. There's a lot of engineering work that still needs to be done. I won't rule it out, but I haven't heard any talk of it. Yeah?
A couple of questions. Speaking of Fermilab, I was used to thinking of the main ring and the starter ring being circular.
Yes.
Is there an engineering reason why the LHC is ellipsoidal?
The LHC is pretty circular. I don't know how much of an ellipse it actually
I was
is.
just looking at the diagram.
The diagram that I showed, that was supposed to be a circle. There might be some distortion on the screen.
Second question, the plasma Wakefield acceleration. Could this have application to a type of advanced propulsion system that has been discussed, the Massinger variable?
So, yeah, could plasma Wakefield be used for propulsion? I don't know. My first reaction is I don't quite see how, because the number of electrons we're talking about, the mass of the electrons being accelerated here is pretty small. I mean, they do have, they do have other space travel propulsion that's based on ions, and that's ion acceleration. That does use plasmas. It doesn't use this plasma Wakefield acceleration. So I don't know. In terms of propulsion, I don't know. Where it could be used is, a lot of hospitals now have small linear accelerators, for radiation treatment, cancer treatment. I think at this point they're probably already pretty economical, but if this technology really matures, it's possible that could lower the price for accelerators in hospitals. Yeah.
Thank you.
You say that you have muons all over the place. I know muons are used for neutrino sources. They're very heavy, 200 times heavier than electrons.
Yeah.
So I heard that there had been some work on using muons to catalyze fusion. Has that gone anywhere?
So the question was, have muons been used to catalyze fusion, to start fusion reactions? And unfortunately, I really don't know. I've heard of a possible muon collider, particle physics collider, but in terms of initiating fusion, I don't know where the advantage would be.
Replace the electrons and let the things get closer together.
I mean, with fusion, what you want to do is get nuclei hot enough so that they and close enough to get together. I don't quite see where muons would come into play, but admittedly, I don't know a whole lot about this either. About fusion.
Neutralize. Muons being heavier, all the ions are much smaller.
You're talking about using muonic atoms.
Yeah.
Ah, okay. That again, I haven't. So this is the idea of replacing at least one of the electrons in an atom with a muon. It would be very short-lived, but it might be, say millionths of a second. But that might be long enough to get a fusion reaction going. Okay, I see what you're saying there. That can make the atoms smaller. Maybe, yeah. But I personally don't know much about it. Sorry.
There's no follow-up on that.
Not that I've heard, but that could just because I don't pay much attention to it. Okay, I'll go over here.
How many cells over the plastic TV detector? Thing is gas. But what's the gas pressure in these cells? Can't you just increase the amount of gas?
To some extent. So the gas pressure is typically around like 80% of atmospheric pressure, up to about atmospheric pressure. The reason you don't want to mess around with the pressure too much is that you don't want these things under high pressure, because if you bump them the wrong way or something, or even low pressure, again, they might either explode or implode. Keeping them around air pressure at least takes that, it mitigates some of that risk. So, but you're right. If you could put more gas into those cells, you wouldn't have to, say, have maybe, you could have less than a 3 millimeter gap between, or less than a 3 millimeter space for the particles to travel through, that's for sure. So one or two more questions, yeah?
Regarding the plasma acceleration technology,
Yeah.
can you only accelerate electrons using this method, or can you use the 4 other particles?
So,
protons?
So you can, so you can do positrons, the positively charged antimatter counterpart of the electron. It's not quite as efficient with positrons. Actually, I think I'm speaking about computer simulations. I don't know if anyone's actually tried it with real positrons, but it's in principle there's no reason you can't do it. With protons, I think it becomes a little bit harder, but I haven't heard much about using it for protons. I'm not sure. I mean, another thing you could do actually is you could use really high-powered electrons, maybe accelerated in this manner, and use those to create accelerating waves, maybe to accelerate protons. So to have kind of a two-stage thing where you speed up the electrons and use that to generate some energy. Put that into protons. Would that be useful? I'm not sure. So certainly electrons and positrons, but I'm not sure about protons. All right. So one more question? I thought I might have seen another. All right.